Okay, we've done 2 already, right? This is our final gas law. What happens when pressure is constant? But temperature changes. I need to, again, redraw my containers. So if you can do that on yours, I will do that on mine. Remember, try and make them about the same size, just so we have the same idea, right, that the container itself is not really changing. Here's my little pressure spigot. 0, 1, 2, 3, 4. Right? And then my other one. You will have to draw, right, a model, actually a few on the test. Okay, so that's why we're spending a lot of time showing what happens. When temperature changes, there's 2 ways it can change, right? The first way is if we cool it down. The second way is if we heat it up. Okay. So let's talk about the temperature change first. What's happening? Which one am I controlling? How much space there is, how much motion there is in the particles, or how many collisions? Which one am I influencing when temperature changes? The motion, absolutely. When it cools down, what's happening to the motion of the particles? Yes, slower, absolutely. Or we're going to say decreases, right? And then this would be faster when we heat it up. Are we good with that? When pressure is constant, what does that mean about the space or the collisions? Which one am I influencing or talking about when I talk about pressure? Collisions. What is happening to collisions if pressure is constant? What's happening to collisions? It should be staying the same, right? So if I know pressure is constant, I have to make sure that what is the same. How do we model collisions again? The x's, right? I have to have the same number of x's in both of these models because pressure is constant. How do I model motion? The arrows, right? Which one's going to have a longer arrow, the slower one or the faster one? The faster one has longer arrows. Good. So then here's my question, right? If the motion is slower and there's the same number of collisions, what's going to happen to the space? If my particles are moving slower, but it still has to maintain the same number of collisions, what's going to happen to the space inside my container? What do you think? It's got to be smaller. Remember, if it's medium speed and medium volume, right, and medium pressure, if I have slower, I have to have smaller. Okay, so I'm going to go ahead and I'm going to drop my lid, right, down to here. How about the number of particles? Should I put less particles in? Yes or no? Did I change the number of particles? I did not. Let's make sure, remember down here, the number of particles. How do we measure the number of particles again? It's the number of dots that we draw in, right? The number of particles, or the moles, are constant. So if I start with 9, how many should I draw here? I should also draw 9. Slower motion, right, means little arrows. Remember, because I have the same collisions, I have to have some, right? So I'm just going to draw little arrows, right, with maybe just a few collisions, maybe 2, to show that it's sort of just a medium amount of collisions. Right? And I draw little arrows with X's for my collisions, right? 2 collisions in that side. Well, if I have faster motion, but the same number of collisions, what does that mean about the volume of the heated gas? It has to be bigger. Right? The space has to be bigger. This increases. I still draw 9 particles, right? Still 9 particles. What's happening with my arrows? It's going to show that there are longer arrows because why? They're moving faster because my temperature has increased, right? Oh, how many collisions am I going to have? 2 because it's constant, right? So you should draw 2 of them bouncing off of the walls, right? But the other ones, right, should be long arrows. Remember, on a test, make sure, right, that I can really tell that your arrows are longer, right, than the others, right? I shouldn't have to be able to guess and be like, is that longer? I'm not sure if that's longer, right? Make it obvious. Okay, but still only 2 collisions. Okay, you have to make sure that you're consistent with these 3, actually the 4 things, right? The space is the volume. The motion is the temperature. The collisions is the pressure. The number of particles is the moles. Good. So here we go. As temperature increases, volume does what? Yes. Think about it like a microwave bag of popcorn, right? Anybody ever eat the microwave popcorn bags? Right? You slide it in and it's totally flat at first, right? But as the microwave starts to heat up the oil and the popcorn and the whatever's in there, what happens to that bag? It's bigger, right? Okay, and they have to measure a certain amount, right? They know how much gas is going to be produced. Otherwise, what would happen if there was too much gas? The bag would actually explode in the microwave, wouldn't it? Okay? If one increases and the other increases, they are what kind of relationship? Yes, directly related. From our lab, this is called Charles's law. The graph, right, looks a lot like Gay-Lussac's, right? Here's temperature, here's volume. There we go. The equation is V1 over T1 equals V2 over T2. One more note. Temperature must be what? Not in degrees, but in, not in Celsius. Yes, Kelvin. Oops. Now I wrote Kelvin. Kelvin. That's a big V. Here's the thing, right? You're like, oh my gosh, there's 3 equations. How do I know which one's which? You don't really have to, because there's one equation to rule them all, right? Like the one ring. Pressure 1, pressure 2. Volume 1, volume 2. Temperature 1, temperature 2. This guy, he's called the combined gas law down here. Because if pressure is constant, that means I can just drop pressure out, right? And when I drop pressure out, does he look like this guy? He sure does, right? And if I drop out temperature, right, like I did in my notes from before, right, these guys here, when temperature is constant, right, when temperature is constant, I can take out the temperatures, and does he look like this guy here? Yes. And if volume is constant, I take out volumes, and who does he look like? He looks like Gay-Lussac. Okay? This guy, he's called the combined gas law, the one equation to rule them all, right? If you look in your reference packet, you will see, hold on, let me get mine, that all of these are there. You don't have to memorize any of them, right? They're all here. Lussac's, Boyle's, Charles, and the combined. If you really needed to memorize one, you should memorize this one because it includes all 3 of them. But you just have to look and be able to reference them. Capiche? Great.